In this video, we want to give a demonstration of how that implicit function theorem is used to find out if the implicit function is defined given some type of capital F equation. So let's start off with some capital F function where capital F depends upon y and x. And let's suppose it takes on the following form: is x squared plus y squared minus 9. And if we set that capital F function, which depends on y and x, if we set it equal to 0, we get our capital F equation. X squared plus y squared minus 9 equals 0. And if we were to graph out that capital F equation, what would it look like? Well, put x on the horizontal axis, y on the vertical axis. And if we were to plot out those different xy pairs that satisfied that equation, we would get a circle with a radius of 3. That would look something like this. And here's the question we want to ask ourselves: is given this capital F equation, x squared plus y squared minus 9 equals 0, is the implicit function where y is expressed explicitly as a function of x defined around a given point? Let's say around the point x equals 2, y equals the square root of 5. So again, we're saying, okay, can you take this capital F equation, can you put y on the left side of the equality and move all of the terms involving x to the right side of the equality and express y explicitly as a function of x doing that? Well, let's see. To answer this question, we have to go through the conditions of the implicit function theorem. And according to this theorem, if these three conditions or requirements are satisfied, we can conclude that this implicit function is defined. Now, the theorem doesn't tell us how to find this implicit function. It just tells us that in principle, it is defined, it does exist. What is the first condition of the implicit function theorem? It says that given our point, that point has to satisfy the capital F equation. In other words, this point has to lie in that circle. So how can we see if that does lie on that circle or not? Put in the value of x into our capital F equation and put in this value of y also into the capital F equation, and we get the following result. 2 squared plus y was the square root of 5 squared minus 9 equals 0. And is that true? Well, we get 2 squared is 4 plus the square root of 5 squared is just 5 minus 9 equals 0, and that checks out. So the first condition, or the first requirement of the implicit function theorem, is satisfied. What's the second condition of the implicit function theorem? All the partials of our capital F function have to be defined at the said point. So if I look at the partial of capital F with respect to y, what is that equal to? We'll go back to our capital F function, x squared plus y squared minus 9. Take the partial of that with respect to y, and we get 2y. And what is that partial derivative of 2y equal to, evaluated at our given point? Remember, y is equal to the square root of 5, so this is 2 square root of 5. And that is some defined value. So therefore, the partial of capital F with respect to y is a defined value. Now we have to also look at the partial of our capital F function with respect to x, and that's equal to, here's our capital F function, the partial of it with respect to x is just 2x. Evaluated at our given point under consideration, well, x is equal to 2, so this is 2 times 2, which is just 4, and that is a defined value as well. So we can conclude that the second condition of the implicit function theorem is satisfied because all of the partials of the capital F function are defined at our given point in question. What is the third condition of the implicit function theorem? The third condition is that the partial of our capital F function with respect to y, evaluated at the given point, which in our case was 2 times the square root of 5, cannot be 0, which in this case it is. It's not equal to 0. So since those three conditions are satisfied, we can conclude by the implicit function theorem that the implicit function, where y is expressed explicitly as a function of x, is defined, given our capital F equation, around the said point, where the said point was x is equal to 2, y is equal to the square root of 5. Now, what does this all mean? Well, if we were to go back to the drawing that we had up here of our capital F equation and graph out that circle, remember what we had here. We had something like this, right? And so let's see, x is equal to 1, 2, and here x is equal to 3. So when x is equal to 2 and y is equal to the square root of 5, we know we have a point on the circle. Call that point A. And if we were to look at a neighborhood about point A, say some type of rectangular neighborhood about point A, then for that portion of the circle contained in that rectangular neighborhood, for this portion of the circle right here, y is a function of x. For any given x, there is a unique value of y. If we only consider this thick portion here of the circle within the neighborhood about point A. Now that, we can find the derivative of this implicit function, the derivative of the circle, so to speak, evaluated at point A. What is that derivative equal to? Well, the derivative dy dx, remember the implicit function that was defined as y equals some function of x, and its derivative dy dx by the implicit function rule is minus the partial derivative of our capital F function with respect to x, the variable downstairs, divided by the partial of the capital F function with respect to the variable upstairs, y. So just substituting what those are equal to, we already solved for fx, which was equal to 4, and fy evaluated at the said point was 2 times the square root of 5, which is equal to, let's see, minus 2 over the square root of 5, and that is the slope of our circle at point A.